Hello, everyone. Sorry I could not be there today. We are going to be talking about how to model using polynomial functions. A lot of companies actually, this is what they do for a living. So if you've ever picked up a Kleenex box or a water bottle or something like that, and you never thought, that's literally someone's job to come up with the dimensions of that box to figure out, what volume would maximize how much it can hold, but minimize the amount of materials required to build it. Like, what is the least amount of cardboard needed to make the largest volume sized box to stuff with Kleenex? That's literally someone's job. And so we're going to kind of do the basics of that today and talk about that. So let's say you start off with a rectangular piece of cardboard that is 20 inches by 30 inches. And what we're going to do is we're going to cut the corners away, and we're going to cut squares from each corner. So if I have this random sheet of paper, I'm basically going to remove a square of X from each side. And I'm going to do that. Okay, I'm going to do that on all four corners. So this would be removing X, 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 X. So I'm going to take X away from each of the corners, and what that produces is basically like a little flap from each side of our rectangle. So now we have like a little, it looks like a really stretched out cross, essentially. And what I did was I took X away from each side. So what was a length of, 20, I now removed X from one side and I removed X from the other side. So what we need to come up with is an expression to represent this flap. And I took X away from this side and I took X away from this side. So now I need an expression to represent the longer flap. So if I'm taking X's from both sides, then that means this longer side is going to be 30, that's the original length, minus the two X's that I took away, that I ripped away. And the shorter side originally was 20 across the whole distance, but again, I took away two X's. So if I take these flaps that I've now created, and this is 20 minus 2X, and this is 30 minus 2X, what I can do, if this was, a company making a box, I would fold up these edges because I know that they're all the same length, and what I just created is a three-dimensional shape with a height, as you can see under my document cam, a height of X. So now I can go from area, which was 20 by 30, to a volume with a height of X. The short side is 20 minus 2X, and the long side is 30 minus 2X. So picking up where we left off, we now have a three-dimensional shape. So if we know the height of our rectangular prism, or box, if you want to call it, is the height of X, which is the corners that we took away, our width is going to be 20 minus the 2X, and our length is the 30 minus the 2X, then we should have a volume of length times width times height. Length times width times height. So our formula for this rectangular prism, which it will ask in letter C, is the height times the width times the length. Now, if we do this by hand, what if I never cut anything from the corners? Then the original shape would be 30 by 20. I never cut anything, so 0 inches were cut away from the corners. So this would still remain 20, this would still remain 30, and 0 times 20 times 30 would produce a volume of 0 because there's no height to the shape. But what if I cut 1 inch from each corner? So remember, I'm cutting X from each corner, okay? So if I do that, I would have 20 minus 2 times 1, which is 18. And I would have 30 minus 2 times 1, which is 28. And 1 times 18 times 28 would give me a possible volume of 504. Well, there's an easier way to go about doing this than having to do it by hand. So if I did this one more time by hand, it would be, what if I cut 2 inches away from each corner, which would make the height of my box 2 inches? Well, if I cut 2 inches from each corner, that's really like subtracting 4 total inches from the short side. It's the same thing as cutting 4 inches from the long side. And so if I do height times width times length, that overall volume increases now to 832. So what you notice is it's starting to climb. Well, I'm not going to do this for this whole box. I'm just going to fill in the numbers. So if I cut 3 inches from both sides, this will now be 14. There starts to be a pattern to it. 12, 10, 8, 6, 4, 2. And actually, if I cut 10 inches from each side, well, it was only 20 inches to begin with. That now means that it would have a width of 0. I basically cut the paper all up. Same thing here. You notice the pattern starting to form, 30, 28, 26. So if I fill in the rest here, and I multiply straight across, so 3 times 14 times 24, what would the volume increase up to? Ooh, now the volume is 1,008 inches cubed. If I multiply straight across in the 4th row here, it's 1,056. And then if I multiply across on the 5th row, it goes back down. And it keeps going down and down and down to eventually back down to 0. Some high point is happening in that vicinity. The maximum volume is happening somewhere in these dimensions realm. And that's what someone's job is, to figure out what is the exact number so that we can maximize that volume. We're going to have our calculator help us with that today, but I just wanted to give you that first idea of like what's happening here. So we only used from 0 to 10 because the width of the original piece of paper was 20 inches. If I'm cutting X from both sides and X is 10, then I've pretty much cut all the paper away. I can't go any higher than 10 because I can't cut away more than what I have. So our our X values, our possible X values are from 0 to 10. So anything between 0 to 10 would be fine. So here's where we're going to utilize our calculator. So if you haven't gotten that out just yet, please do. What we're going to do is we're going to type this entire equation in our y equals screen. So go to your y equals screen on your calculators. And we are going to type that equation in our y equals screen. We might have to adjust our window to be able to see the entire graph, because if I just hit zoom 6, which is like our standard 10 by 10 window, I probably am not going to see anything. Yep, there it is. All I see is this little line, and that's not helpful to me. So go back to this table. Our height, remember, goes from 0 to 10. So I'm going to make my window X values go from 0 to 10. And my volume are my Y values. Now I know my approximate maximum is 1,056. So I'm going to change my Y values to go from 0, and let's go up to like 1,200 just to be safe that we see everything we need to see. So let's adjust our window on our calculator. So window, and make it go for the X's go from 0 to 10. And change your Y min to go from 0 to a Y max of 1,200. And now hit graph, and we should see a much better image of what we're trying to find. There we go. I'm going to draw the little sketch of that. Just like a little mountain here. And for us to be able, it says based on your equation, what is the maximum volume of the box and what X value would give us this maximum volume? So for us to find the maximum volume, which is going to be right over here, we are going to hit second trace. I'm going to try and not get that glare on the calculator. Second trace, option 4 gives us that maximum point. There's my blinky spider. Move it to the left bound of the high point, so somewhere on the left. Move it somewhere on the right. And somewhere in the middle, and hit enter. And that should give us the exact decimals. This says round to the nearest hundredth in the directions. So my max point is 3.92, comma, 1,056.31. Now the question comes into play, okay, It's asking for 2 answers, and obviously my coordinate point has 2 things. You just have to remind yourself, what did you plug in? In my y equals screen, I said y is equal to the equation, and the equation is representing volume. So when I'm looking at an x and a y coordinate, the y is the volume. The x was the amount that I'm cutting from each of the corners. Okay, so this is how much I cut, the amount cut from each corner. That's what it's asking. What is the maximum volume and what is the value of x to produce this volume? So these are, in this problem, both of my solutions. So let's try another one where we have to cut the corners again. You were planning to make an open top rectangular box from originally an 8 by 15 piece of cardboard. So we originally have 8 by 15. I'm going to cut squares again from the corners and fold up the sides. So if I cut squares of x from each of the corners again, what I will come up with, or what I will find, is it's almost the same exact setup as the last one. The long side will be 15 minus 2 x's because I cut an x from this side and an x from this side. And the short side here will be the original short side minus the 2 x's as well. If I fold the flaps up, I make a 3-dimensional box. One side is the longer side, one side is the shorter side, and now the height is what I cut away. So that's your x. So our volume formula for this is height, width, length, or length times width times height, but I'm just putting it in a more aesthetically pleasing order. Now this time I don't have that little chart to use as a tool to guide me, so we're going to use the table in our calculator. There's no reason why we can't use that as a guide to help us figure out our proper window to see what we need to see. So go to your y equals screen, type in this new equation. Okay, so this is going in your y equals. And so I'm going to type x, parentheses, 8 minus 2x, and 15 minus 2x. And now instead of just hitting graph, because remember we adjusted the window so it's not going to match, go to your table. So second graph, and obviously we can only talk about positive values, so get out of the negatives if you have to, and look at, this is perfect. If you look at your y values, it goes 0, 78, 88, 54 back down to 0 pretty darn quickly. By the time x is 4, I'm out of space. So I'm going to make my window x values go from 0 to 4 because that's exactly what my calculator says it does. From 0 to 4. Starts at 0, goes up, comes back down. And so if 88 is right now my rough maximum, go a little bit bigger just in case it gets higher than that. So I'm going to go up to 100. So adjust your window now. Go to window, 0 to 4 instead of 10, 0 to 100 instead of 1,200, and hit graph. There's our picture. It looks identical to the last one, but we're going to get different answers. So here's our picture. And again, let's see what it's asking for us. What is the largest volume of the box you could make round to the nearest tenth? So all they want this time is the volume, which remember is a y value. So let's find out. Second trace maximum, blinky spider on the left, blinky spider on the right, blinky spider in the middle, and hit enter a third time. I'm going to write down the whole thing. So round to the nearest tenth is 1 decimal place. So 1.7 comma 90.7. And so my answer for this problem would just be the y value. So 90.7 would be the maximum volume. And this was labeling in cubic inches, so inches cubes. All right, so if you're starting to get the hang of it, of course, I'm going to throw a wrench into your plans because number 3 is different than the other two. So this time it says from each corner of a square piece of sheet metal, remove 9. It's different because before we were given the dimensions of whatever the material was. This time I don't know the lengths of the original piece, but it's a square. So if something is a square, I know that each side is the same. And since I don't know it, when we don't know something in math, we usually label it with an X. So if the original side is X, and I'm removing 9 centimeters from each of the corners, okay, I'm removing 9 centimeters from each of the corners. The original length was X. Well, now this little flap here is going to be X minus 18. And actually, so is this one. And so is this one. And so is this little one in here. Okay, all 4 of those flaps, because it was a square, are all going to be X minus 18. Now, if you're thinking, where did she get 18 from? Just remember, 9 plus 9 is a total of 18. So if the original length was X, and I took 9 from this side and 9 from this side, I took 18 away from the original length. So if I draw this as a 3-dimensional shape, this side would be X minus 18, this side would be X minus 18, and the flap is your height. So the height is now 9. And what's different about this one is before we were trying to solve for the volume, it actually tells me 144 cubic centimeters. Use your knowledge from geometry last year. Cubic is a volume measurement. So this is giving you the volume. So if I want to write a formula, volume equals length times width times height, the volume is 144, the height is 9, the width is X minus 18, and the height is the length is X minus 18. It's asking what should the dimensions of the sheet metal be? Remember, the sheet metal was our original square, aka they're asking for you to solve for X. Now, I don't recommend actually using your calculator on this problem at all. I actually think we can solve this one algebraically. Because if I have the same factor written 2 times, I should be able to write that as a single factor squared. If I want to solve for X, well, I would divide both sides by 9. There's no reason why I can't do that and get the numbers a little bit more reasonable. Here's a 16. Okay, and then now you're thinking, oh, this is starting to look a lot more familiar because if I want to solve for X, I would square root both sides. But when I square root both sides, when I square root, I should say something squared, I need a plus or minus. So I'm going to rearrange this so that it looks a little bit more normal for us. X minus 18 is equal to positive or negative. Square root of 16 is 4. And that sets up 2 cases. One is X minus 18 equals positive 4. The other one is X minus 18 equals negative 4. One of my answers is 22. One of my answers is 14. And you're like, wow, so there's 2 possible answers for this one? Well, remember that this is giving you what the original piece of sheet metal's dimensions were, and that was X by X. But then I went and I have to remove 9 centimeters from both corners. So if I have an original piece of sheet metal and it's only 14 by 14, based on this answer, is there a way for me to cut 9 centimeters from both corners on that? Hopefully you all agree that that's not possible. So this answer gets rejected, and the only possible solution is 22. That's the end of our notes. Please work on the homework, and I will be back tomorrow. Bye.